Vodcast 9D is about gas stoichiometry. So how can we incorporate those gas laws into what we did last unit into the stoichiometry unit? First, we have to assume a couple things. We're going to assume that we're working with ideal gas law conditions, so those very low pressures and the high temperatures. That way, we can use the ideal gas law to calculate things unless you're told otherwise if the conditions change. If it's under standard temperature and pressure, remember that our temperature is 273 Kelvin, and our pressure is equal to 1 atmosphere. So your conditions will always be given. So where do I start? Same spot. Stoichiometry has to do with the mole ratios. So step one, I have to balance the equation. I need those mole ratios, so I need the coefficients after it's balanced. You're going to have to convert those to calculate moles of reactant or product, because then we can use that moles and plug it into the PIV-NERT, or the ideal gas law equation. My moles can be plugged in for my N. Now these problems can also include a limiting reactant. That would be stretching it really far. And you still need to be comfortable with the snowman conversions between grams and moles. Let's try a couple. Here's our equation. Mercury can be produced through the decomposition of mercury 2 oxide. Mercury 2, that's a 2 plus. Oxygen is a 2 minus. That would be HGO. Decomposes means breaks down into, what are its parts? Mercury and oxygen. Oxygen is always a diatomic, so it's O2. So to balance that, I would need a 2 over here. 2 to 2 to 1 is my coefficient ratio. Write a balanced reaction. Got it. Assuming the complete decomposition of 4.10 grams of mercury at STP, what volume of gas can be produced? Okay, where do I start? First, I have grams of mercury. Mercury oxide. I'm given 4.10 grams. I want to convert that to oxygen. Start with what you're given. 4.10 grams of mercury oxide. First step, grams. Thinking of our snowman, we have to go grams to mole. 1 mole of HGO is equal to, oxygen is 16, mercury, looking on the periodic table, is 200.59, so my mass is 216.59 grams per mole. 216.59 grams. Now I want to get to oxygen, so I need my mole ratio. 2 moles of HGO is equal to 1 mole of oxygen. Using our calculators to calculate this, 4.1 divided by 216.59 divided by 2, 0.009, 3 significant figures, 46 moles of O2. But it didn't ask for moles of O2, it asked for the volume of O2. Since it says STP, remember, 1 mole equals 22.4 liters at STP, so I can convert moles into liters using that conversion. 1 mole equals 22.4 liters, so I just multiply by 22.4, and you should get 0.212 liters of O2. Now, for number 3, what if I change the conditions? What if the conditions are changed to 400 Celsius? Got to convert that to Kelvin. 673 Kelvin and 740 torr. Converting that to ATM. 740 divided by 760 should be 0.97 ATM. Now I can't use my conversion. 22.4 liters is 1 mole because this is not at STP. I have to use PV equals nRT. So what's my new pressure? 0.97 ATM. Volume is what I'm solving for. Equals N, my number of moles we calculated as 0.00946 moles. R, constant still the same, 0.08206 liters, atmospheres, moles in Kelvin, and my temperature was 673 Kelvin. So, Kelvin will cancel, moles will cancel, atmospheres will cancel. I'll be left with liters. Punching that into our calculator, I'm going to get a number for this right side. And then I'm going to divide by 0.97 ATM, which will get me volume all by itself. 0.00946 times 0.08206 times 673 Kelvin. Divide by 0.97. My new volume is 0.54 liters. Again, this is of oxygen gas. 0.54 liters of oxygen gas. I'll do another practice one with you. We have a different equation this time. Solid sodium bicarbonate, sodium Na bicarbonate or hydrogen carbonate, HCO3, 1 plus 1 minus, they balance out, reacts with hydrochloric acid, hydrogen and chlorine plus 1 minus 1, to form a solution of sodium chloride, table salts, NaCl, carbon dioxide gas, CO2, and water, H2O. If we look at that, 3 oxygens, 2 hydrogens, 1 chlorine, it looks to be balanced. Now, the question asks, calculate the mass of sodium hydrogen carbonate. How much of this do I have to start with to produce 2.87 liters of carbon dioxide? Here's my volume. At temperature, 25 degrees Celsius, plus 273, 298 Kelvin, and 2 atmospheres, which is my pressure. So, now first I have to calculate my moles before I plug it into the equation. I have to use PV equals nRT. I'm solving for N if you want to rearrange the equation first. N equals, getting that all by itself, PV over RT, or pressure, 2.00 ATM, times my volume of 2.87 liters, divide by R, 0.08206 liters, and atmospheres over mole and Kelvin, and the temperature is 298 Kelvin. Double check that all the units cancel. Kelvin, Kelvin, liters, liters, atmospheres, atmospheres. My answer is going to be given to me in moles. When I punch that in the calculator, I get 0.232 moles, and that's of carbon dioxide. Now, I want to convert moles of carbon dioxide, which is what I have, back to mass of sodium hydrogen carbonate, or sodium bicarbonate. Moles of CO2 0.232 moles of CO2. It's nice that my ratio is 1 to 1. So 1 mole of CO2 is equal to 1 mole of NaHCO3, but it doesn't ask for moles, it asks for grams. 1 mole of NaHCO3, looking on the periodic table to calculate the molar mass, 84.01 grams. Solving that out, punch that in your calculator, you should get 19.5 grams of NaHCO3 is what you would need to produce all of this carbon dioxide at those specific conditions for temperature and pressure. So you can either use the equation first to calculate moles and then plug it into the ideal gas law, or we can do it reverse. We can use the ideal gas law to calculate moles and then use stoichiometry to convert back to grams. You'll have several more practice problems like this on your next worksheet. Last thing, for all of our calculations, we assumed that the gases are ideal, low pressure, high temperature, but really there are real gases, not ideal gases, because who behaves ideally all the time? We try to, but it doesn't quite happen. Real molecules, real gas molecules, they do take up space, they do interact with each other, things can change. There is a correction factor for this. You won't get into this unless you're taking AP chemistry, so we're not going to talk about the correction factors for the ideal gas law. We're just going to follow the ideal gas law, but just so you know, not all gases are ideal. They don't quite behave according to all these gas laws, but you won't get to study that unless you take AP or chemistry in college, and then come back and we'll talk about all those details.